Welcome to this lecture series in Chemical Reaction Engineering 1. We will continue with the next topic, that is tanks in series model. We have seen dispersion model, and it has advantage that the correlations for flow in real reactors invariably use that model. All the correlations for the flow in real reactors are used up. On the other hand, tank in series model, it is simple. It can be used with any kinetics and it can be extended without too much of difficulty to any arrangement of compartments with or without recycle. So relatively simple model. So we'll see the pulse response experiments and residence time distribution. So this theta I is the dimensionless time T by Ti bar. Ti bar, this is the mean time. I indicates the number, that is theta 1 is equal to T by T1 bar, first reactor, second reactor and nth reactor. For nth reactor it will be theta n is equal to T by Tn bar. Okay. So this is the dimensionless time based on mean residence time in each tank. Then we have dimensionless time, which is based on mean residence time in all n tanks. So all n tanks means subscript will not be there, simply T bar. So theta is equal to T by T bar. So for individual tanks or reactors and overall for n tanks, we have defined these dimensionless times. Now in our experiment, what we do, these are the C1, C2, C3, C4 different. This is the concentration leaving this first reactor, concentration leaving the second reactor. These are tracer concentrations, not the reactant. It is non-reactive material. So this is nth tank. So mean time for all n tanks will be simply n into Ti. So if n is equal to 3, so this is 3 into this 3 tanks, T1, T2, T3. So n into, that is n is number of tanks, and this T1 is equal to T2 is equal to Ti and V1 is equal to V2 is equal to Vi. Equal volumes. Okay. All the tanks are of equal volume. So this theta I is n theta, or you can say n is equal to theta I by theta. So theta I dimensionless time is n times theta. So theta I bar and theta, this is equal to 1. And any particular time, at any particular time, if this is valid, then E theta is T bar into E. This we are taking from the chapter 11. E theta is equal to T bar E. So T bar into E, this is dimensions of time, this is dimensions of time inverse. So this is dimensionless variable E theta. So wherever you have theta in the subscript or theta, that is used for dimensionless variable. So it can be dimensionless time, can be dimensionless excitage and so on. So we'll consider number of tanks here. So for first tank, consider a steady flow rate of V meter cube per second of fluid in and out of the first of these ideal mixed flow units. Ideal mixed flow means we are considering that the mixing is proper. Okay, it is well mixed. So first unit is of volume V, second is of volume, this is volume V1, then V2, V3 and up to Vn, and all are equal. So we can say V1 is equal to V2 is equal to Vn is equal to Vi. I is counter. Similarly, for T, T1 bar is equal to T2 bar is equal to Ti bar. We inject at time t is equal to 0 the pulse of tracer into the vessel, which when evenly distributed in the vessel has its concentration C0. Okay. So at the instant we introduce this and we assume that it is evenly distributed at the concentration C0. This is tracer concentration non-reactive material. So at any time t after the tracer is introduced, we'll write the material balance. Input is 0 because continuously you are not sending the tracer in the reactor or not adding the tracer in the reactor. So it is added at once. So input rate is 0. V into C1. What is V? V is the volumetric rate and this is concentration. Okay, so volumetric rate say meters cube per second and this is concentration moles per meter cube, meter cube, meter cube will cancel out and what we get is moles of tracer per second. So leaving the reactor, V is constant throughout. Whatever is entering in the first reactor at steady state, same is leaving in the from the last reactor. So this V is constant. So V into C1. And on this side, this is the rate of change of tracer concentration, d dt of C1 in that tank 1 multiplied by volume. So this is moles per unit volume per unit time. So multiply by volume. So this will also become moles per unit time. So V1 into dC1 by dt is equal to minus V into C1. That is the material balance for the first tank or first reactor. So now here we are considering it as a tank. We are not considering any chemical reaction. Only RTD studies. When C1 is the concentration of the tracer in tank 1, so we separate the variables and integrate it. So dC1 by C1 is equal to V by V1. So capital V by V is tau, or in this case it is T bar, mean residence time, and here we are using for the first reactor. So for first reactor it is say T1 bar, and as the volumes are equal anyway, this is going to be equated later on. But just to distinguish between reactor 1, 2, 3 and so on, will maintain this till the sum up for nth reactor will maintain this. So you integrate this, you get C1 by C0 is equal to e raised to minus T by T1 bar. So this T will be there. So minus T by T1 bar will be on this side, and ln of C10 by ln of C1 by C0 on this side. You take antilog, we get C1 by C0 is equal to e raised to minus T divided by T1 bar. So you can substitute Ti bar also because all are equal. That we will do later on. So here, if we plot C by C0 as a function of time, area under the curve gives T1 bar. So T1 bar into E1. This is again dimensionless. T1 bar into E1. So we know for E curve, E into T represents area under the curve. So T1 bar into E1 is equal to e raised to minus T by T1 bar. That means this C1 by C0 is T1 bar into E1. So this is dimensionless. This dash indicates dimensionless. And this is for n is equal to 1 reactor. Now we consider second reactor, second tank. C1 enters and C2 leaves. So material balance in the reactor, rate of change of C2 dC2 by dt into V2. What is entering? V into C1. What is coming out of the first reactor entering the second reactor, and what is leaving the second reactor? V into C2. Units are again moles of tracer per second. So here you note that V1 is equal to V2 is equal to and so on Vi, and similarly T1 bar is equal to T2 bar, and that is equal to finally Ti bar. So we can substitute all of these things. So V1 dC2 by dt, V C1 is C0 into e raised to minus T by T1 bar minus V into C2. Okay. So divide by this V1. So if I divide this by V1, I get T1 bar in the denominator. Okay, because V1 by V is tau or T1 bar. So when I divide by V1, this is T1 bar. Similarly, this should be divided by V2 to get T2 bar, and V1 is equal to V2. So we write T2 bar. Okay, and these are same. Finally, we are going to write it as Ti bar. So second reactor. So this is the differential equation of the form dy by dx plus py is equal to q, where the solution is y into e raised to integral p dx, and that is equal to integral q into e raised to p dx plus constant. So this you can evaluate. So integrating factor e raised to p dx, we have to write there this. So okay, this you forget, this we don't need. Integrating factor here is p. What is p? Ty is C2 by T2 bar. So 1 upon T2 bar is P. 1 upon T2 bar and dt. So e raised to integral 1 upon T2 bar by dt. Integral dt is t. So simply e raised to t by T2 bar. So C2, y is C2. So this C2 into integrating factor, integral q. What is q? This right hand side. C0 by T1 bar into e raised to minus t by tau, that we have written, multiplied by same term again dt plus constant. This is the solution. Now we have to evaluate the constant. So before that, evaluate this integral. So this is minus t by T1 bar and this is plus t by T2 bar, and T2 is equal to T1. So this will cancel out. Okay, because T2 is equal to T1. So this goes. What is left? C0 by T1 bar dt. Integral dt is t. So C0 by T1 bar into t plus constant. T is equal to 0. At t is equal to 0, C2 is equal to 0. Because in the tank at time t is equal to 0, it is just before addition of C1. So constant will be 0. So this is 0. At t is equal to 0, value of the constant is 0. So solution is simply C2 into e raised to minus t by T2 bar, and that is equal to this term. This constant is 0. So this I can write as C2 by C0. C2 by C0. All we will write in terms of ratios. T by, so this is C2. So what we have done here, this T2 is equal to T1, T1 is equal to T2. So I will write this as T2 bar, because I want to maintain a proper notation for this. You can see here, for C1 by C0 we have the T1 term. So here we want this T2 term we have here, and this will also write as T2. Okay, so that there is the consistency of the notations, and this we can do easily because replacing T1 by T1 bar by T2 bar only because the tanks are of equal size. Okay, so this C2 by C0 now can be written as T2 bar into E2. Like earlier we have written C1 by C0 as T1 bar into E1. Okay, and that is equal to this right hand side as it is. This is again dimensionless for n is equal to 2. So for nth tank we have to write, so you can write as for third, fourth and so on, but we will see the terms can we arrange or can we write for the nth tank looking at C1, C2, C3. Now for third tank, fourth tank and so on, so differential equations are complicated. They have to be solved by Laplace transforms. We will not bother about solving those differential equations. We have written here C1 by C0 what we got, C2 by C0 what we got, and T1 E1 this term, T2 E2 this is for n is equal to 2, and similarly for third tank you can derive C3 by C0. You will get here T square by T bar T3 bar cube, T3 bar squared. So this square e raised to minus T by T3 bar, and here into 2. Okay. So we want to write now for nth tank. T3 E3 will be this right hand side, T square by 2 into T3 bar square multiplied by e raised to minus T by T3 bar. This is again dimensionless for n is equal to 3. So we have for n is equal to 1, n is equal to 2 and n is equal to 3. Okay. Now if this n is equal to nth reactor I want to write. Okay. And this E1, E2, E3 we can write as E1 will be e raised to minus T by T1 bar divided by T1 bar. Here T1 bar in the denominator. Here it will be T2 bar square in the denominator. And numerator we don't have T here, that means T raised to 0. Here we have T, cubic term. Transfer this on this side, so write E3 is equal to 2 into T3 cube. Here we have T square and e raised to minus T by T3 bar. So all we have written. Now check the terms one by one. About T first. Here T is not there, means T raised to 0. N is equal to 1. So 1 minus 1 is 0. Here we have T. N is equal to 2. 2 minus 1 is 1. So T we have. N is equal to 3. T raised to n minus 1 means 3 minus 1 is 2. T square. So I can write for T, T raised to n minus 1. Here we have T1, T2, T3. So, and all is equal to, we can write that is equal to Tn. But all these terms are equal to Ti. So I am writing here Ti. Then here, what we get in the denominator? T1 bar term we'll look at. T1 bar raised to 1. Here T1 bar, T2 bar raised to 2. Here T3 bar raised to 3. Means raised to 1, raised to 2, raised to 3. Means Ti bar. So T1, T2, T3. This Ti is the counter. So we can write it as Ti bar raised to n. So we got this. And here in the denominator, n is equal to 1. Okay. Here n is equal to 2, n is equal to 3. So when n is equal to 3, we have 2 here. Okay. So if I write n minus 1 factorial, means 2 factorial is 2. N minus 2 factorial is 2 minus 1. 1 factorial is 1 in the denominator. And here n, 1 minus 1 factorial, 0 factorial 0 is also equal to 1. So I can write these terms, and for fourth tank, fifth tank, this will be valid. So simply what you have to do is, if you want to write for fifth tank, so this will be 5 minus 1 T raised to 4. Here 5 minus 1, that is 4 factorial, and this will be Ti bar raised to 5. So you can write like this. So for nth tank, we can write E is equal to T raised to n minus 1 e raised to minus T by Ti bar divided by n minus 1 factorial Ti raised to n. So this I have reproduced from the previous page for n is equal to n. Now just to write in some convenient forms, we'll multiply this by, because we are familiar with this ti bar into e, this becomes dimensionless. Okay, so if I multiplied by ti bar, I can write ti bar into e. Here you multiply by ti. So t raised to n minus 1, e raised to minus, this terms remains as it is, n minus 1 factorial as it is. Here we have ti and here we have ti raised to n. If you transfer this ti here, it will be ti raised to minus 1. So if you combine, this will be simply ti raised to n minus 1. So we have t raised to n minus 1. In the denominator, I get ti raised to n minus 1. So I will write this ratio t by ti bar raised to n minus 1. Okay. That is what we achieved from multiplying by this, and also on this side we are getting a dimensionless term. 1 upon n minus 1 factorial as it is, and e raised to minus t by ti bar as it is. Okay. Now t bar is n times ti bar, that you know. Here the variance or variance we have used, this is equal to t bar square by n, t bar square by n, and we can write ti bar from this as t bar by n, and also variance as n into ti bar square. So if I know the mean and variance, I can find out the number of tanks to be employed in series. Okay. This same thing again I want to write. Now this ti bar can be written as t bar by n. Okay. E into ti bar is replaced by t bar by n. Here this ti is replaced by t bar by n raised to n minus 1. This ti bar is replaced by t bar by n. So t bar by n. So it becomes minus n into t by t bar. This is 1 upon t bar by n raised to n minus 1. Okay. If you take this n in the numerator, it is n raised to n minus 1. And if you transfer this on this side, it is n raised to plus 1. So minus 1 plus 1 cancels out, and you get n raised to n term in the numerator, and the bracket will be simply t by t bar raised to n minus 1. So t bar into e is t by t bar raised to n minus 1. This n raised to n term is here, and rest of the terms remains as it is. So why we are doing it? We want to write in this dimensionless forms these terms. You know theta I we have already defined as t by ti bar. E theta I, this ti bar into e, we know this, we have written for t1 bar into e, t2 bar into e, and so on. So this is dimensionless, so I can write this as e theta I, where theta is used for dimensionless term. So ti bar e is equal to e theta I. Ti bar e, which we have already written here, t by t bar raised to n minus 1, and here e raised to minus t by ti bar. So this t by ti bar term is theta I raised to n minus 1, and this again same term minus t by ti bar can be written as minus theta I, and this theta I square is equal to n. This is variance in the dimensionless form. Then e theta. Like we have written E theta, you can write E theta also. And for that, this TIE is to be multiplied by N. Okay, so this is for theta I, and for N reactors, if this right hand side if you multiply by N, this E theta I you can write as E theta. That means N theta I is equal to E theta. Okay, so this is multiplied by, and now you can look at the terms and collect the terms. So E theta N Ti into E. So N multiplied by this Ti into E. Okay, this term. So this right hand side simply multiplied by N. Rest of the terms are as it is. So E theta we have written, and this we have multiplied by N times. So E theta is N into this N we have theta I can be written as N theta. Okay, this is for 1. So for theta I is equal to N theta. Then this is raised to N minus 1 divided by 1 minus, and this theta I is again written as N theta. Okay, so theta I is equal to N theta, that we have written here, and this gives the definition of variance as, here it is N is equal to sigma square theta I, so for each reactor, and in totality it is sigma theta square, and this is equal to 1 by N. So at the end we'll tabulate this and also look at these expressions. So you have to keep this in mind. T bar is N times Ti bar. So from this, when this subscript I is there, this indicates for each tank. So T1, T2, T3, T4 and so on. So like N tanks you have, and Ti is equal to Ti are equal. That means T1 is equal to T2 is equal to T3 is equal to Tn. So N times Ti is simply this mean residence time in the system of N tanks in series. This we have defined. So this dimensionless time theta is T by Ti bar. Okay, Ti bar is nothing but T bar by N. So this Ti bar is written as T by N. So we can write it as N times T by T bar. That means theta I is equal to N times theta. Similarly, theta if I want to write down, this is T by T bar, and T by T bar is N times Ti. N times Ti. So all this, nothing to be confused. Only keep in mind that theta, this is the dimensionless variable for time. When you write I here, this there will be I, and when subscript I is not there, this indicates dimensionless time for the system of N tanks in series. This is for individual tank, theta 1, theta 2, theta 3 and so on. Like for those, this mean residence time will be T1, T2, T3 and so on. So all these equations we have written in the 4 forms. Okay, all these for N tanks in series. So we have solved for tank 1 first, taken material balance and integrated the equation written in terms of first one C1 by C0, second one C2 by C0, third one C3 by C0 and so on. And finally we have written for n tanks. This is T bar into E for the system, Ti bar into E for individual units. This is T by T bar, and this will be naturally T by Ti bar. Raised to n minus 1, raised to n minus 1, it is there. This is n raised to n for n tanks. This is for individual. So 1. Then this e raised to minus t by Ti bar. This is for single tank. For n tanks, this is minus t into n by Ti bar. Okay. T bar is n into Ti bar that we have substituted here, and this tells us that variance is T bar square by n. N is number of tanks. That means if you find mean time and variance from RTD studies, n is equal to T bar square by sigma square. So number of tanks to be employed you can find out. Same thing, these two expressions, one for individual system and one for the total system of n tanks in series. Same thing is written for this in terms of dimensionless variables. E theta I, okay, and E theta. This is for single individual all systems. So you can E theta 1, E theta 2 and so on. And this is for total system of n tanks in series. So this we have already discussed. This is just reproduced from there. And here this theta I square is equal to n, sigma theta I square is equal to n when variance is calculated for this in dimensionless form. And variance for the system, this is 1 by n. We will use mostly these expressions. Okay. Now these are the curves. You can see this is theta. Okay. It is T by T bar or T by n times Ti bar. So this is for the complete system and this is depends on how many number of tanks you have. Okay. So here for n is equal to 1, n is equal to 2, 3, 5, 10, 20. So you can see here for n is equal to 1 almost it is spread, n is equal to 2 there is a spread, n is equal to 3 this is being narrowed down, n is equal to 5 it is still the spread is less, n is equal to 10 the spread is still less, and n is equal to 20 you can see it is narrowing down, the spread is still less, and this is E theta calculated as a function of theta. Okay, so you can plot this. This I have plotted in Excel by calculating E theta for each curve. Okay, this you can do exactly same curves you will get. So I have just placed it for comparison. So this will be an interesting exercise if you would like to do. This has nothing to do with your examination and all that. It depends on your interest. Okay, so you can reproduce this. You know, because we have derived this equation, we have found out this equation and its validity is to be checked. So this is the only way to do it. Then this is E theta I, and for n is equal to 1, 2, 3. So this is a different kind of representation. Same thing again. This has been done in Excel. You can also calculate and you will get exactly similar curves.